Today, we're looking at a paper called MHLA, Restoring Expressivity of Linear Attention via Token-Level Multi-Head.
It's from a team at Peking University and NVIDIA, including Qiwei Zhang and Yi Huang.
And the core problem they're tackling is something called global context collapse.
Exactly. Standard linear attention is great. It gets you from quadratic NaN2 complexity down to linear, but the way it does that is by compressing all the keys and values into one single global summary.
And in doing that, you just kill all the diversity in the representation.
You kill it. So the solution here is MHLA, or multi-head linear attention.
What they do is instead of one big global summary, they partition the tokens into blocks and then use a learnable multi-head mixing mechanism.
And that's the key insight. It brings back what they call query condition selectivity.
Meaning different queries can actually retrieve different contexts again, sort of like softmax attention, but you're still in that linear complexity world.
The results are pretty wild. A 41% improvement in video generation, 12.6% on image generation, and on high-res tasks, an 8.2x speed up over flash attention.
So global context collapse. That, it sounds dramatic, but I think for anyone who's actually tried to get linear attention working in a production model, it feels pretty accurate.
It does. You see these papers, they promise the world linear scaling, and then you try it, and the model just it hits a wall. It stops learning.
So why is this paper different?
I think it's because it's the first one to give a really solid theoretical diagnosis for why all the previous attempts have failed.
Right. We all know the context, transformers are dominant, but self-attention, the $dollar part, is the bottleneck. It just doesn't scale.
Not for high-res images and definitely not for long videos. It's just computationally impossible.
So the industry for years has been chasing this idea of linear attention. The pitch is always the same. You drop softmax, use a feature map, and then you can reorder the matrix multiplication.
Exactly. You get to pre-compute this global key value summary. You calculate TTVA, and you get a single summary matrix, maybe times deal dollar in size.
And then every single query just looks at that one pre-computed summary.
It's elegant on paper. It gets you to dollar complexity. But here's the catch that this paper just nails. They call it the fixed size bottleneck.
That dollar times dollar matrix.
Yes. And D dollar, your future dimension, is usually pretty small, like 64 or maybe 128.
It's tiny.
It's tiny. And standard linear attention is trying to compress the entire sequence, whether it's 100 tokens or 100,000 tokens, into that same tiny grid.
So wait, if I'm processing a 5-second video clip versus a full-length movie, the model has the exact same amount of, memory space for the context.
Precisely.
Yeah.
And that's what leads to what they prove is rank deficiency. The rank of that attention matrix, which is kind of a proxy for how much distinct information it can hold, is strictly bounded by dollars.
So as your sequence length dollar grows, the matrix just doesn't have the capacity. It becomes rank deficient.
It's like, I don't know, trying to zip file the entire internet onto an old floppy disk. Eventually, the compression is so lossy that everything just looks like a blur.
And that's the context collapse.
That's it. The paper shows the entropy of the attention distribution just goes flat, becomes uniform. The model can no longer find the needle in a haystack because the entire haystack has been squashed into one uniform block of hay.
Which is why those generative models can sometimes give you those, washed out textures or weird hallucinations. They literally can't focus.
They can't.
Okay, so let's talk about the fix, MHLA. Now, usually when you say multi-head in a transformer, we're talking about splitting the channel dimension.
Right, splitting the embedding dimension dollars into, say, 8 or 16 heads. MHLA is different. They split the token dimension.
Okay, that's the crucial shift. So walk me through that.
So imagine your input sequence. Let's say it's an image that's been flattened into patches. MHLA partitions that sequence of patches into a non-overlapping blocks. You can think of it as just a grid.
So instead of one global summary for the whole image, you're now making smaller local summaries for each block, each part of the grid.
Correct. But then you have an immediate problem, right?
Yeah, if my query only looks at its own local summary, I've lost the global context. I've just reinvented, local windowed attention.
And you've defeated the whole purpose. So how do the blocks talk to each other? This is the secret sauce. They introduce a learnable parameter, a matrix they call the multi-head mixing matrix.
The mixing matrix.
Think of it like a dynamic routing system. For each query block, this matrix learns a set of coefficients that decide how to combine all those other local summaries.
So it's not a fixed rule, like block 1 always talks to block 5. It's learned.
It's learned. And this is what restores what they call query condition selectivity, which, is the holy grail.
Right, because in softmax attention, every query gets to decide what it pays attention to. In standard linear attention, every query sees the same blurry blob.
And in MHLA, query block A can construct its own version of a global context by learning to mix, say, a lot of block 1 and a little of block 5, while query block B might construct a totally different context that emphasizes blocks 2 and 3.
So it's mimicking the adaptivity of softmax, but it's doing it with linear operations.
It's a two-stage process. First, the block selection happens via the mixing matrix, and then within those selected blocks, the regular kernel handles the fine-grained token-level details.
Okay, let's talk cost. As an engineer, whenever I hear we split things and then we mix them, my brain just hears overhead. Does this actually stay linear?
It does, but you have to be smart about the hyperparameters. The total complexity is 1ND2 plus M2D2.
Okay, so let's break that down. ND22 is the standard linear attention cost we already know.
Right, and the second term, M2D22, that's the new part, that's the cost of mixing the M blocks.
So the key is that as long as the number of blocks squared, $2, is less than or equal to your sequence length non-dollars, the whole thing is still dominated by the linear term.
Exactly. And in practice, you'd never make every token its own block. For an image with 4096 tokens, you might have 64 blocks. 642 pilled is way less than 4096, so the cost is negligible.
What about the implementation? This is a huge hurdle for new attention mechanisms. You see things like ring attention that sound great, but then require you to write custom CUDA kernels, which is a nightmare.
That's a massive selling point here, this mixing operation. It's just matrix multiplication. It's standard GEMM.
So it runs efficiently on an H100 or an A100 right out of the box.
Yes. No exotic modules. And it avoids the other trap, which is adding things like depthwise convolutions.
Oh, right. I've seen those papers, the focused linear attention family. They basically just slap a convolution layer on top to force the model to look at its neighbors.
It's a Band-Aid. It works. Kind of, but it adds parameters, it complicates things, and you're forcing a specific inductive bias onto the model.
But MHLA is proving you don't need that external crutch. You just need a smarter way to route the information that's already there.
Exactly. It's a much cleaner, more native attention solution.
All right, let's get to the benchmarks. Theoretical efficiency is great, but does it actually run faster?
So they tested this on a diffusion transformer, DITS2, at a 4096 resolution.
4K, that's a heavy workload.
It's massive.
Yeah.
And standard self-attention with flash attention was barely chugging along at 0.9 images per second. Basically unusable.
And MHLA?
7.4 images per second.
Wait, that's an 8.2x speedup.
An 8.2x speedup, and crucially, without the out-of-memory errors that you'd constantly be fighting with self-attention at that scale.
Okay, speed is one thing, but quality is everything. How did it do on ImageNet?
They used a vision linear transformer architecture. The tiny variant with MHLA hit 82.6% top one accuracy.
That's solid.
It is. And what's interesting is that it clearly beats the other linear attention baselines, and it also outperforms Mamba-based models in this specific setting.
Beating Mamba on an image task is a really strong signal right now.
It suggests that this block mixing approach might be better at capturing 2D spatial relationships than the purely sequential state of a state-space model, at least for vision.
But the generative tests, that's where the rubber really meets the road. Classification can be forgiving, but generation exposes every single flaw.
Totally. So they tested on DiTXL, extra large. And there's this fascinating insight in the paper about scaling laws.
Oh, yeah.
A lot of these linear attention models rely on hacks, like conditional positional encodings, to work at all. And the paper found that while those hacks help small models, they actually hurt performance on a big model like DiTXL.
They introduce noise at scale.
Exactly, but MHLA works without them. And on DiTXL, it matched the FID score of full self-attention, around 19.1 as seen. Meanwhile, vanilla linear attention was way behind at 28.63.
Wow, a 9-point gap in FID that's the difference between a photorealistic image and a blowy mess.
It's night and day, and it fine-tunes fast. They adapted it to SANA, a text-to-image model, and it recovered the original performance in just 2,000 steps.
But the real stress test, the one that makes this paper feel like it's about the next generation of AI, was the video generation task.
The 1.2.1 model, 1.3 billion parameters, and the sequence length was 31,500 tokens.
31,000, that's something like 81 frames of video. That's deep into the danger zone for quadratic attention.
And it's the death zone for vanilla linear attention. They tried to train it. The loss curve just went flat. It completely failed to train.
The context collapse was too extreme.
It couldn't connect what was happening in frame 1 to what was happening in frame 80. That tiny dollar times D dollar bottleneck was just too small.
But MHLA?
MHLA converged. It trained successfully, and achieve performance on par with flash attention,
And the inference speed.
2.1x faster.
In video generation, cutting your inference time in half is just pure ROI. That's cutting your compute bill in half.
It changes the user experience, too.
Yeah.
It's the difference between waiting 30 seconds for a clip and waiting a full minute.
I want to loop back to the theory for a second. We mentioned rank deficiency earlier. They actually provided a mathematical proof for how MHLA fixes this, right?
They did. They formally proved that the rank of the attention matrix in MHLA actually grows additively with the number of heads.
So you're no longer capped by that small feature dimension, dollars. You're effectively restoring the resolution of the attention map.
Exactly. And they show this visually with entropy analysis. The attention maps from standard linear attention are just flat. High entropy, a total blur. The MHLA maps are sharp and spiky.
It can find the needle in the haystack again.
Which they also tested. They ran it on NLP benchmarks. On the long bench suite, which has things like multi-document QA, MHLA actually outperformed Mamba.
That's really ironic because Mamba is, specifically designed for that kind of long context retrieval.
It is. But it suggests that maybe the fixed state of an SSM can still struggle with pinpoint retrieval compared to an attention mechanism that can dynamically route queries to specific blocks of text.
So if I'm an ML engineer listening to this and I'm trying to build a video generator, is this actually ready to use?
The code is on GitHub. And because it's just using standard GMs, it seems to be a remarkably simple drop-in replacement. If you're hitting OM errors with your high-res models, this looks like a very, very strong candidate.
It really feels like we're watching linear attention finally graduate from being an academic curiosity to something that's actually production viable.
I think so. For years, there's been this assumption that the quadratic cost of transformers was like the price you had to pay for intelligence.
The price of admission, yeah. To be smart, you have to compare everything to everything else.
But maybe not. MHLA suggests that maybe softmax was just a computationally inefficient way of implementing that intelligence.
And if you can achieve that same query condition selectivity, that ability to focus with just linear operations and some smart block mixing,
then we've been overpaying for compute for almost a decade.
That is a provocative thought to leave you with. Is a fundamental requirement for intelligence, or was it just a temporary implementation detail? Go check out the paper. Thanks for listening.
See you on the next one.